Hi everyone, this is Farida, Mona, and Sama, and this is our project for brain tumor segmentation. This is our table of contents. Our first point, which is the proposal summary and the problem statement. Our problem statement is brain tumor segmentation using MRI scans for patients and detecting whether they have a brain tumor or not. This is the related work that we covered previously. And this is our chosen dataset for the brain tumor segmentation, which is called BRATS and the 2020 because it's the 2020 version. And this dataset includes 369 patients, where each patient has 155 slices of their brain scanned, and each slice goes through 4 channels. This is an example of the 155 slices, and this is an example of the 4 channels, including the ground truth in the end. So for our baseline model, we chose the two-path CNN, which uses a cascading architecture where two inputs are taken from the image, and these inputs are assembled after several activation functions, and then the output of one model is input into the next one, and then the output is the classification whether this brain has a tumor or not. For our evaluation metrics, we use die-square, which measures the overlap between the ground truth and the prediction, the sensitivity, which is the true positive rate, the true negative rate, and the F1 score, which is a combination of the precision and the recall. And for our implementation, we did the following.
So we did 3 main trials for our implementation to be able to um, reach an optimal solution to our model. We've tried 369 patients using only 5 slices instead of 155, and then using 2 channels. And this trial failed, and I'll show you later why. And then we tried 369 patients with 5 slices and 4 channels, which also failed. And then we finally tried having 71 patients and using all the 155 slices and all the channels, and this is what worked for us. So these are the attempts that led to overfitting. As you can see, the model accuracy is 1, the loss is 0, and the precision and recall are 0, which shows that it has done overfitting when we only used 5 slices, and therefore we decided to use all the 155 slices but reduce the number of patients.
Another pre-processing step that we did was the skull stripping that we previously mentioned. It basically removes the redundant parts around the brain, leaving only the pixels that contain the image for the brain, and it's useful to for improving the model robustness. Moving on, we've also did the CAMI and contour edge detection, so that we were able to crop and resize the image for a better quality image.
So for our baseline model, we implemented two-path CNN, as I previously mentioned. We started by training and testing, splitting our data into training and testing sets using the 80-20 classic split. However, we had limitations due to the size of the data because, as we previously mentioned, we only have 71 patients. We used ReLU and sigmoid activation functions in dense layers and using the sigmoid layer in the final layer because this is a binary classification problem. We also used same padding and batch normalization for more effective analysis. And lastly, we optimized all our models using Adam. So this is the summary for the two-path CNN model. And as you can see, most of our parameters are trainable, which means that the model is more catered to our dataset. And these are the performance metrics and graphs for the two-path CNN. And as you can see here, the accuracy improved across the epochs. And as you can see, it ended somewhere between 82 and 84%. And the model loss kept decreasing and it approaches 0. For the model recall, it started at 70% and it increased to somewhere around 80%. And the same thing occurred for the precision. The next step was adding the attention gates to the two-path CNN to improve the model's performance and focus on the most relevant regions in the image only. And this is the summary for this model. And as you can see here as well, that most of our parameters are trainable. So this is more customized for our data. So we predict more improvement and higher performance metrics. And this is the unit.
Moving on, another model that we've also used was the UNET, and it's a CNN model that is specifically designed for the biomedical image segmentation, and it's effective for segmenting regions of interest, and it was introduced in 2015. And here is the model summary, and as you can see as well, most of the parameters are trainable, which is a good indicator. However, we weren't able to fully run the model due to the computational time, and therefore here is just one epoch from the from the model when it was running, showing that the accuracy was around 50%, the loss was around 3%, precision and recall were around 50% as well. Moving on, we've done an ensemble of both the two-path and the UNet together to capture the advantage of both, where the two-path CNN captures the multi-scale and hierarchical features that focuses on local and global details, while the UNet uses the encoder-decoder model and skip connections to preserve the spatial information, and it's essential for pixel level segment level tasks. And that allows for better generalization and less overfitting, where each model has different inductive biases, and the ensemble may learn different aspects of the data. Here's the summary of the model. And as you can see, it's very tall due to implementing both together, and as well, most of the parameters are trainable. Yet we weren't also able to do it due to the computational time.
Moving on, we implemented the class activation mapping, where we basically try to interpret the model. So the CAM explains which regions of the image contribute the most to the network's prediction of the tumor presence, and this is how it was implemented. And then, so these are the output that we were able to reach. These are the parts in the brain that the CAM focuses on for prediction when the brain has a tumor, and the other image shows the part it focuses on when the brain doesn't have a tumor. And so the result is overlaid to highlight the regions that the model considers the most relevant for the classification, and this is very helpful for interpretation. Finally, for the conclusion, so far we've implemented the skull stripping. We were able to pre-process the data. However, we run into the issue that it has a high computational time, and we had RAM issues. And so we also implemented the two-path CNN. We implemented a mini batch gradient descent. And we currently are in progress working on the UNet, and as well as attention gates on the two-path CNN, which is expected to enhance the model. And then we expect to have an ensemble of both the attention gates two-path model and the UNet, and this will reach a better accuracy, hopefully. And finally, we were able to implement the CAM, which shows which part of in the brain the model focused on that affected the prediction the most. And this is the progress so far. As you can see, we were able to do over 50% of the work, and this is the work in progress. And this is the team contribution. Thank you.